Hello everyone. So in today's lecture we have to start a new topic, that is support vector machine, SVM. In previous classes, two algorithms I have covered. Currently we are studying supervised category of machine learning, where we are available with labeled data. In supervised, we do have regression problem and classification problem. In regression, the algorithms which we have seen is linear. That was our main algorithm, as the target available in regression is continuous in nature. Along with that, in order to tackle overfitting, we also learned about lasso ridge. While elastic nut is a combination of lasso and ridge. Okay. We have also discussed about polynomial regression. So these things were covered in regression. In classification, I taught logistic regression. Logistic regression, that's a classifier, but it is present in linear model. Okay. Now we need to start another machine learning algorithm, that is named as support vector machine. Well, machine, the term used here, that will be in context of ML only, machine learning only, nothing more than that. However, the prior two terms, support and vector, these two have some meaning. Okay, support means to assist someone, to help someone. Okay, so here I am taking assistance. Vector. Okay, so we do have the vectors which are assisting or helping us for some reason. So for vector, I should be having data points. Okay, I should be having data points for the vectors to make a vector. Obviously, this is your 2D plane. Okay, this is a point, this is a point, this is a point. All right, so I can make vectors. All right, v1, v2, v3, three vectors I can make. Currently, our algorithm says that support vectors, not vector, support vector. So, to whom we are giving support, to whom we are giving assistant, and what is the reason for it? Okay. So, support vector machine is an algorithm, and in this algorithm, we can perform regression and classification both. Okay. So, support vector machine is an advanced algorithm where regression and classification can be performed. However, the previous algorithms which we have seen, one is used for regression, another is used for classification. But now I am having combined ability in an algorithm which is named as SVM. So I can perform support vector regression, I can perform support vector classifier. So from SVM only, I am getting two algorithms which can perform regression and classification specific task. Again, my point to convey is support vector. Well, you do have, let's talk about classification first. Classification. In a classification, we are having categories or classes. Let us suppose you are having class A and class B. Okay, let me plot them by considering a data set. Let us suppose this is my data, okay, and this is feature 1, this is feature 2, this is my class. So let us suppose these points belong to class A, these points belong to class B, these points belongs to A, these to B. Okay. So if I make a plot between F1 and F2, obviously you will be having the data points. Here also we are having the data points. Okay, fine. Now, according to the classification, this is how the data points are present. And you can see from here only these points belongs to a particular class, let us suppose A. These points belongs to a class B. Right now, such kind of distribution of data points you are seeing. Okay. So I want to classify, I want to separate A from B. This is the distribution which you are seeing. We as a human can understand, okay, this is class A and this is class B. But how machine will understand that this is A and this is B? We have to make a machine to understand between the classes. So obviously we have to devise an algorithm. We have to write a technique. Currently we are having SVM. So what SVM do? SVM obviously right now classification now that's your problem. Decision boundary. This you have studied in logistic regression also. Decision boundary. If you need to classify the data points, you have to make a decision boundary. So my SVM will make a decision boundary that I am calling as hyperplane. Okay, a name to it, hyperplane. Now, sir, how you will make this decision boundary? That is what entire SVM support vector classification do perform. Making a decision boundary is what your algorithm needs to perform. Sir, in logistic, you do have a sigmoid function and you are calculating probability there. You told about log of odds. So far, what you have explained in this sheet, you haven't told about any formula. You haven't told about any probability. You said that we have to create a decision boundary to separate the classes. That will be called as hyperplane. So, how this decision boundary will be created? Now, if we again check the name support vector, that means that means there will be points in your plane that will be helping us in creating a decision boundary. So, I am making that in form of these dots, like it's just an way to explain those points, those data points which are here and which are here of your distribution. Those data points who define those data points who define class boundaries are called as support vectors. Not every point is called as a support vector. No, these are not support vector. But those points which define the class boundaries, they are called as support vectors. So I can make a vector on them. Okay, these are the vectors. From here, class A starts. From here, class B starts. Now, assume same thing. Okay, we are not saying that from here A starts and from here B starts. No, I am saying from here A starts, from here B starts. Now, assume that's what happens. We do have borders between countries. Okay, and on border, let us suppose this is a border. There is a fencing. Obviously, the people don't live exactly on the border. No? They are just somehow what away from the border. They start living from here also. So there is some gap. No? We keep it. There will be soldiers. There will be patrolling. Those who safeguard the borders. So there is some gap, and we say, okay, from here region of A, or okay, from here region of A starts, and from here the region of B starts. So in order to mark that from where A starts and from B starts, how to know or how to understand? Obviously, here soldiers of country B will be present, here soldiers of country A will be present. They are the support vectors. These people are keeping the boundaries safe. Okay. Same concept is applied here in support vector machine. And if I am get to know about these maths, I can make a decision boundary which can classify between A and B. Okay. So that's what the concept says. Currently, I have shown you a data set which is having two features, F1 and F2. So you do have right now 2D. In 2D, in order to separate, in order to separate, a line is required. A line is required. Okay. And if we are having 3D, then a plane is required. Okay, fine. So, and they are called as the separation, the line or the plane, they are called as hyperplane. Okay. So a line will behave as a hyperplane for 2D. A plane, a plane that is 2D will behave as a hyperplane for 3D. If you are having n dimensional data, then n minus 1 dimensional hyperplane will be there. Okay, just like if you have a 3D, to divide this 3D, I require a plane that will divide it. That will divide. This is a 2D plane. A 2D will divide 3D. A line will divide 2D. A line is divided by a point. That's it. Got it? So, our goal in support vector machine, remember, our goal in SVM is to find optimal hyperplane. That is what our goal. You have to find a hyperplane that will clearly divide class A from class B. Okay, now let me share my entire screen. But that's not an easy task. That is not at all easy. Why? See, it's not easy because distribution of data, that is important here. There are two cases which I can put here in distribution of data. One, I can say linearly separable. Another is non-linearly separable. Okay, linearly separable and non-linearly separable. Linearly separable is the easiest of the case. If you can separate class A from class B with a line, it is easy case, and that's what I call as linearly separable. But if you can't separate classes with the help of a line, then it is non-linearly separable. That is a complicated case, and we can have these complications not mandatory over 2D. We can have over 3D, we can have over 1D also. For example, this is your 1D, and we are having these points of the color, and let me have, okay, let me have, I need to change the pen. Let me have a different color also. Okay, so if on this 1D, this is how the points are distributed. I can't separate them with the help of a line. Not possible. If you cut this line, then red will mix with your wallet here. If you cut like this, here red will mix with the wall. So such kind of distribution of data is linearly inseparable. Now if you see, if you think, sir, previous algorithm was logistic regression algorithm. Sir, there we haven't thought too much. We haven't thought about the distribution of the data, sir. We just took log of odds. We were having probability. Okay, just probability we are considering. We are taking log of odds. And we do have a sigmoid function. We are saying 0 and 1. We took a threshold zero point 0.5. It's general. In general, we took a threshold zero point 0.5. Greater than zero point 0.5, class 1. Less than zero point 0.5, class 0. But sir, where is the distribution of data? We haven't talked about the complexity. If we are having linearly separable also, so obviously one will belong to class, okay, one of the data point will belong to class 1, another will be belonging to class 0. Okay, so that too also on the basis of probability. So I think logistic regression was dealing with a very simple analysis. If the distribution of data is something like this, even we can have much more tough distributions. I will be showing you ahead. So if I want to classify them, separate them, I think I require much more advanced algorithm, and that's what I am seeing in terms of SVM. Because SVM says that you have to make, if you want to classify, you require a hyperplane. Okay, I'm not talking about a probability. You require a hyperplane. This will help in classification. And making a hyperplane is tough if we check the distribution, because linear is okay, non-linear is tough. So what SVM can do in such cases? See, our goal again to find optimal hyperplane. Optimal means what? Again, let me show you. This is the distribution of data point. This is the distribution of data point, class A, class B. If you separate class A from class B like this, okay, it is also a hyperplane. It is classifying A from B. But I will not call it as optimal. No. This is not an optimal hyperplane. An optimal hyperplane is a hyperplane where support vector of A, support vector of B, they are just like in a uniform distance from class, from the decision boundary. Okay, this is class A, this is class B. Here you can see the decision boundary or the hyperplane is closer to A, it is farther from B. So this is not optimal. I can have many hyperplanes which can classify A and B, but it's not mandatory that they are optimal. Okay, they are not optimal. An optimal hyperplane, that's what we need to find, is it should be like in this way. This is optimal. So obviously, sir, this is again a challenge. Previously you said okay, separated, but separation may be separate you have to do, but in separation also you have to take care that it should be optimal. Sir, one problem you have already shared, non-linear. This is a challenge. So for non-linear SVM do follow a trick that is called as kernel trick. The one which I have shown you above, this case, where it is difficult to separate the data with the help of linear. What SVM do? It will transform the data into higher dimension. That means initially you are having data points on 1D. These are different colors data points. It will transform this 1D to 2D. Like it will like this. It will look like this. Now these will be the red points. These will be the red points. And these are my purple points. I can now separate. This is hyperplane. Okay, that's what I can do. I can separate from A and B by applying a trick. So there are many things in support vector machine. Did you understood the introduction of SVM? What I taught right now? Do you have any doubt? Please let me know. Any doubt so far? Okay, you don't have any doubt. All right, fine.